Hello everyone. Thank you for joining our webinar today. I'm Thomas von Larcher. I'm Managing Editor Engineering of the journal, and I'm helping to run the meeting today. So today we have Professor Michal Nowak from Poznan University of Technology with us, and Professor Nowak is guest editor of the topical collection combining combining numerical computation and geometric modeling. After the talk, we will have time for questions. So please type your questions into the checkbox as we go. And as an option, you can unmute yourself after the talk and ask your question. So with this, I hand it over to Michal. Michal, it's a pleasure for me to have you in our series today, and the floor is yours.
Thank you, Thomas, for the introduction. So my presentation is entitled Biomimetic Structure Optimization Method. And I would like to show you that it is possible to use new paradigm for shape and topology optimization. And I decided to use very simple code to make possible the application of the results. So first, I would like to start with the structure optimization problem concern the shape and topology optimization. Then I would like to show you the standard approach to compliance minimization. I suppose you're acquainted with this for sure. And then I would like to show you that we can use some biomimetic approach. So I would like to explain what do I mean by biomimetic approach. Then we can just compare these two approaches and say something about some advantages of this new approach. So that for different topologies we are able to we obtain different topologies for different load magnitudes and also different topologies for different materials. So let's start with some basics. So the goal, our goal is to maximize the stiffness of the structure. So it means we have to minimize the compliance functional. So of course, this such a problem has no solution if there is no additional constraint. And usually this additional constraint is volume constraint. So with this state equation, we can look on our problem like on this picture. So omega represents here the domain of the elasticity system. U, the displacement, the V0 is the given volume, so this is the constraint. And gamma 0 is the part of the boundary with Dirichlet condition, and gamma 1 is the part of the boundary loaded by the attraction forces. And what is for us much interesting is the gamma V, the part of the boundary subject to modification. So we have to modify this structure to obtain the stiffest structure. So the standard approach we use or people use in the whole world is based on the SIMB approach, so solid isotropic material with penalization. And many codes use this approach. And so LTER and so on, and you can find this approach in almost every code for topology optimization. So more or less, this is the same here structure of these codes. So first of all, you assume some material distribution for the whole domain, and this material distribution assume that the material is distributed evenly in the whole domain. And then you switch some in some way the properties of this material, and then you try to decide of these properties to be real material, so the density is going to 1, or voids, so the density of this fixtures material will go to 0. In the end, you should obtain in this domain a code by Ole Zygmunt in the paper 99-line topology optimization code written in MATLAB. You're able to just take this code or write it again and replicate this result represents. I think is important thing. So how it works, this code, and how is the approach to the topology optimization in this case. So first of all, we want to minimize the compliance, and then we immediately go to finite element methods. So instead of here of the functional, we obtain the sum of energies included in the elements, and then we is the main point here. And then we go to some heuristic scheme for upgrading the values of the density of the finite element material. So how it works to obtain the minimum, so we have to start with the Lagrange function, and we have here the compliance, and here is the Lagrange multiplier, and the constraint in this case, the constraint is the volume constraint. So after the differentiation, we should obtain the 0 of this term. So we obtain this equation here, and when we divide both sides, we obtain the term. We can introduce the term BE, and BE is more or less some wide for deciding how to change the properties of the elements. And the main assumption is like this: if the element have higher energy, so the compliance is higher, so we want to make this element stiffer. If there is no energy, or the energy is low, so we want to make this element less stiff. And everything is possible to compute. This is the assumption that for each element, we assume that each element has unit volume, and in this way we can compute everything for looking for BE. And here you can observe this is the Lagrange multiplier, and this Lagrange multiplier is we have to find it just to fulfill the volume constraint. In this case, the biosectioning algorithm is used to find this value to fulfill this condition. So here you can observe how it works. So the elements with higher energy are closer to 1. So this is the 1 means the real material, and elements when in which the energy is lower, we just put it close to 0. But how is the results of such an approach? Here you can observe it, that in this example, we start with 2 different forces. So the domain is the same, the volume constraint is the same, but the force is different. But the result is identical. So why? Because of this assumption. So the assumption is the same. So we have to we're starting with some assumption, and in the end, the assumption must be fulfilled. So it means that starting the computation, we know already the final volume of the structure. So this is a little bit problem, because when we start with different forces, we obtain the same solution. So of course, this is the question of this Lagrange multiplier. And of course, it was observed that here is the work of Grégoire Euler, that increasing the Lagrange multiplier means decreasing the width of the structure. But the assumption of the volume constraint produced such a results, nothing else. So what is this Lagrange multiplier? Could we say something more about this term? And we just started some justification or something like this, that this term is very important in the area of compliance minimization. So I am going to present a work done together with Professor Sokołowski and Professor Rzechowski. Here the main role will be played by shape derivative. So we start, of course, with this Lagrange function. Then we rewrite the state equation in the weak form, and we just we want to take the shape derivative of both this equation, and then assuming that at the stationary point this equation should hold for any vector field Vx on gamma V, we can conclude that for the stiffest design, so to have fulfilled the stiffest design assumption, the strain energy density here along this gamma V surface should be constant. And this strain energy density is just the Lagrange multiplier. So the Lagrange multiplier is something more than just a multiplier. It's a very important thing, because if you produce the structure, if you are able to design the structure with the strain energy density which is equal on the structural surface, it means that this the compliance of the whole structure is minimized. So this is also important. But how to realize in practice? Yeah, this is something strange, that this is no way for writing the equation to obtain such a result. But I would like now to look on in the biology. So the trabecular bone surface adaptation. This is a very interesting phenomena. That bone remodeling, this is a special kind of bone inside the heads of long bones, like here in spine and in many spine elements and many other elements of our organism. You can find such a kind of bone. It is called trabecular bone because of very special structure of small trabeculars, so beams like very small in micrometers, denominated in micrometers, and this structure is extremely complicated. But what is important from the mechanical point of view? So this bone is built in reaction in some mechanical stimulation. So the tissue mechanosensation, we can say, is important. And what is also important, everything is on the surface. So why this is on the surface? Because you need some blood to make this process possible. So you have to put the cells, and the only way is do it by blood. So it was observed many years ago that the bone can rebuild the important thing like strength properties. And look here, after the bone is broken, the new structure is completely different from the regular structure, let's say. Why? Because here and here you can observe completely different forces, external forces. So the internal structure of bone change in the reaction and for change of external forces. And this observation is called Wolff's law. So every change in the function of bone is followed by certain definite changes in internal architecture and so on. So this observation is the base for our studies, that maybe it's possible just to mimic this process and use some ideas from nature, looking for some optimal structure. And how it works in the reality. So first, this is the trabecular, about 40 micrometers. Oh, so this is quite complicated structure. Yeah? And first, part of this trabecular is removed by osteoclasts, and then in this area, osteoblasts build new tissue. So this new tissue formation depends on the external forces. And here on the right side, you can observe that in, let's say, 3 years, you whole your internal bone are completely removed and replaced by a new tissue. But this process is the reaction for external forces. So external forces are very important. So I would like to show you now some model by Huskis, Rimmerman, and others, so-called the regulatory model. So this model just described the biological phenomenon. So this is nothing. There is no connection with the mechanical engineering. So this area, when we can observe this remodeling process, so new bone creation, is called basic multicellular unit, because everything here has a sequential is in a sequential of reaction for many different cells. So osteoblasts removed material, osteoblasts produce new tissue. And this model is called the regulatory model because there is the regulation. So this is the main assumption is some homeostatic strain energy density. So also the same here. You can look on this structure as a structure which is stimulated, mechanically stimulated, and you have to measure this level of the stimulation, and the measure of the stimulation is the strain energy density. And the main assumption of this model is that there exists some homeostatic strain energy density. It means that there is the perfect balance between the resorption and the new tissue creation. And this model, more or less, is just the observation of nature, nothing more. Yeah, but how it works, you will see in the moment. But there is another assumption. So the assumption is called the lazy zone assumption. It means that bone is lazy in change of mechanical stimulation. So I will show how it works. So we have two processes. Bone gain and bone loss. So we have to model this. So bone gain, it means that we will obtain more dense areas of trabecular bone, and bone loss mean that we will obtain less bone and change this density of bone. This is the regulatory model is able to answer. So first of all, we have to measure the stimulation. So we will measure it with strain energy density. There are different, of course, possibilities, but this is what was chosen by Huskis. And this C means this is the homeostatic value which produce the same level of density, or not level, but just the same density of bone. So it's 0 here. So there is no bone gain and no bone loss if we have this value C. And now lazy zone. So if we change a little bit the mechanical stimulation, so in the with the direction of higher strain energy density on the opposite direction, this little change is called just lazy zone. So everything what happened in these two positions are assumed that this is the homeostatic value of this bone remodeling. If we have the strain energy higher, like this, we can observe the bone gain. And if we have this energy lower, we will observe the bone loss. But how it works? Let's assume that we have the stimulation in this area BD. So nothing happened. Yeah. So just the density of bone remains on the same level. But if we produce some more mechanical stimulation, so we go here, and what happened? There is the bone gain is observed. So what does it mean if we observe the bone gain with higher level of strain energy density? So we go back to this lazy zone because we have more or dense. More dense bone, and with the higher stimulation, we just go better here to the better area. Let's say for the bone. And if the energy is lower than this lazy zone here, so we will observe bone loss. So what does it mean? There is less bone, so we go back to the lazy zone because this less stimulation with bone loss will produce the circumstances to go back to this lazy zone. So more or less, the whole regulatory model works like this. If the mechanical stimulation changed, the system reaction is like this, that if some area of trabecular bone is out of lazy zone, the system wants to put this area back to the lazy zone. So the ideal situation is that everything, so whole structure is inside the lazy bone. So the strain energy density is close this homeostatic value. So this is what we want to observe from the nature, and this is what we called the biomimetics. So there is one value of the strain energy density which is good or the best for the structure. So what does it mean? That if we are able to find this value, this value will be important to have it in the whole structure. Strain energy density is denominated in pascals, and also the Lagrange multiplier is denominated in pascals. So now we are able to modify the standard SIM approach. So the modified approach just switch these two terms. So the volume constraint, which is fixed here in the standard approach, and we have to find the value of the Lagrange multiplier to be in line with this assumption. So we switch the roles. And now our assumption is the Lagrange multiplier, and we say, okay, the Lagrange multiplier have to be constant, like it is in nature, in this process of bone modeling, and then we will obtain the volume. But the volume is not assumed. The volume will result from the process of optimization. So how it works? If you take this code, 88 lines or 99 lines from Ole Zygmunt, you start with some assumption volume constraint, and then you change the Lagrange multiplier. And we just skip this process of finding the Lagrange multiplier, and we put the information about this value immediately to the code. So the change is relatively small, and the code works like this: that now we have one assumed value of Lagrange multiplier, and the volume you can observe here change, and the volume is just the result of the computational process. So if you observe here the upper picture, this is the original approach, and you can observe that this is the Lagrange multiplier here, and this is the change of Lagrange multiplier. And look here, if you go to the solution, so there is no change in the Lagrange multiplier. So this is a very important thing. If you stop the computation in the standard approach, the Lagrange multiplier is constant. And here, this is the modified approach. The results are exactly the same. Why? Because we just put this value of Lagrange multiplier into the code and let the volume just be the result. And the volume, the result of the volume was exactly the same, like in the original approach, the assumption of the volume constraint. So they are completely the same systems with these two terms which play different roles. And why different? Because if you assume now the Lagrange multiplier value, if you change the external forces like it was presented before, the results are different, not the same. The volume are different. For 500 newtons, there is less material than for 1,300 newtons. But this is not the most important thing. The most important is when you look here, there are different topologies. So the different topologies, this is just the reaction for the different load magnitude. So the system works completely different. Yeah? The same when we use different materials. So for steel is the different result, and for aluminium we just put the Lagrange multiplier on the lower value, because this is obvious that aluminium has the properties which are not so good, like it is in case of steel. So also the reaction is good, let's say, or in line in our intuition. If with the same forces you use steel, your result should be completely different when we switch to aluminium. Of course, we need more aluminium for the same forces. And what happened here, also the topologies are completely different. Okay, so this is more or less I wanted to say about this comparison of these two approaches. So the Lagrange multiplier is important. So you can check it in this paper, justification of a certain algorithm for shape optimization in 3D elasticity, published 3 years ago, and we use it for the optimization system. This assumption. Yeah? So we just put the information on the structural surface that it should be just the one value of the strain energy density. And we produced very similar results to the same approach, but of course they are a completely different approach because there is no volume constraint. Yeah? And another, it was just the first biomimetic term here. So this biomimetics means there is the one value of strain energy density on the structural surface, and if you obtain such a surface structure, the structure will be optimized, and then the stiffness of the whole structure will be minimized. But another biomimetic approach, or the second biomimetic area is the lazy zone. So the lazy zone is called the memory of bones. So the bone is able to remember our activity, and this is very important because when you are playing ball or skiing or jumping or something like this, you produce the information about the mechanical stimulation of your bones. And this information remains inside the lazy zone. So we now I would like to show you that we can use it for a multiple load problem, because of course our bone is just the answer for many different loads or different load cases, and the structure is one. So how to produce as a good structure? So we use the assumption about the lazy zone. So instead of just producing the information or change the value of the strain energy density directly, we just want to minimize the deviation from this value for the whole structure. And with this assumption, we can minimize just this functional here, and here is the strain energy density for the area under consideration, and here is Lagrange multiplier, which is assumed to be constant. And when we minimize this functional, we obtain the optimal structure. So by means of lazy zone. So if we minimize it, we just produce the structure which whole area or whole surface will be inside the lazy zone. So this is just the observation from the nature. So we take the shape derivative of this term, and we obtain such a term here. And if you observe it, everything in brackets. So if this expression in brackets is negative, then we should add material on the structural surface. Otherwise, we should just remove this from this area a little bit of material. So we do it like it was in case of BMU. So we just take a little bit material, or just add a little bit material in the area. We measure the strain energy density there, and we decide what to do. And this strategy will lead you to the structure which the distribution of the strain energy density along the structural surface is constant. And here you can observe another term, this kappa. This is the the surface curvature, and this curvature is also important. You can observe it here. If you put this dependency of the curvature, your solution is quicker and better than without this term. Of course, we can now exploit this lazy zone concept. Yeah? So here you can observe two different load cases. You can rotate this square to the right or to the left, or clockwise or counterclockwise. Counterclock, and this is also the one solution which is rather rare. There is the solution which we can now use as a for the comparison. Yeah. So this analytical solution for those two load cases. And this is our system. Yeah, there is no assumption about there is no we don't put together some different solutions for load case 1 and load case 2. So this is just the process of remodeling. We can see here the process of remodeling. So different load cases produce some energy distribution which the system try to introduce to the lazy zone. What is important, the solution for one load case and for the another one are completely different. So this is not possible to compile the right solution, the solution which is in line with the analytical solution, having two different solutions for one load case and another one. Okay, so we also put this optimizer into the aeroelasticity environment. So here you can observe how it works. So we have some information about the pressure distribution on the wing surface. Then this pressure distribution is used as a load for the optimizer, and we change the internal structure of the wing, and then we go back to the CFD solver, and the position, the deflection of the wing is different. If the deflection is different, also the CFD results are different, and the distribution of the pressure on the structural surface is different, and so on and so on. So we have here three elements. So one, this is the CFD solver, and another one, this is CSM solver, and the third part, this is the optimizer based on this biomimetic approach. What is important in aeroelasticity, that every step, this is the different load case. Yeah. So if you want to obtain the solution, the good solution for aeroelasticity, you have to introduce the many different load cases. And this approach, this biomimetic approach, is very, very good, because every step here can be completely different, and the whole process of optimization can run. Okay, so this is what I wanted to show you. So what is important here, that there are two biomimetics points. First of all, this is the Lagrange multiplier, which is one value for the material. So I don't know how it is, of course, exactly, and how the value should be assumed, which value should be assumed, but it must be like this, because this is just observed in the case of bone. So in case of other mechanical, other materials used in mechanical design, we have to find these values. I think it could be similar than von Mises stress that this is something characteristic for the material. So maybe also this Lagrange multiplier could be also be put in the tables, and for this material and for this material we can choose the value of this Lagrange multiplier and start the optimization having this value as an assumption instead of volume constraint. What is also nice in this approach, so the domain independence. So we don't, if you start the standard, in the standard approach, the topology optimization, you have to assume the domain. Yeah? If you a little bit change the domain, the whole process should be repeated, because this 40% of the domain means that if your assumption is not only 40 or 50% of volume, but also this volume is the assumption. If you change this domain, your computation have to be repeated. So in this approach, there is no problem. If you start, you can start with the configuration you want. There is no problem to start with the existing solution, or to start with the whole domain filled by the material. Then functional configuration during the process of optimization, it means that there is no fictitious material. Yeah? So there is no problem with some filtering, or there is no problem with with the decision if this density of material should be put it as a real material, or should be put as a void. There is no problem, because we still have the definition of the real material. Yeah? And then the possibility to solve multiple load problems. So this is immanent thing inside the method. So there is no need for additional action when you have different loads. Or if you change the load, you can immediately change the solution. Okay, so now we try to introduce this method into the industry. So we work with EDAC engineering. This is the company which want to use this method for the additive manufacturing and for the construction of limited short series of cars. And if you want to find more presentations or more information about this method, please look on the Cosmo Projector EU. This is the website that you can find some information about this method, some presentation concerning the aircraft industry, and so on. So thank you very much for your attention. If you have any question, I will be happy to answer them. Thank you again.
Thank you, Michael, for this very nice and interesting talk. It was very nice to see a tour on your ongoing research on structural optimization methods. And yeah, we have time for questions. So if you have a question, please unmute yourself and ask your question. So I have a question, Michael, regarding the optimization method. I mean, I understood the methods must be appropriate for multiple independent load issues, right?
Yes.
So what are, or can you summarize the challenges? I mean the example of the trabecular bone. This example is, or this model is has a very sophisticated structure, right? So I mean it's a network of beams, let's say. So what can you summarize the challenges to yeah, implement the methods or to apply the methods to such complicated structures.
Yeah, the bone is a good example. Yeah, that the structure is the form of the structure is the reaction for the external forces. Yeah, and in mechanics or in mechanical design, you try to find some structure which is normally you have I don't know 5, 6 forces. This is all. And if you put this, let's say 5, 6 forces, your structure will be the answer for them, yeah, and it will be relatively simple. But in bone, your structure, your cortical bone, so this is what is outside the structure, is stimulated by many different muscles and other points when the forces are introduced into your system, yeah? And also the whole cortical bone just react a little bit for the external forces. So the mechanical stimulation of the internal part of your bones are extremely complicated. And this is this form of trabecular bone is just the reaction of this extremely complicated stimulation. Yeah? And if you put the same rule to the mechanical design, it was presented here. Oh, so yeah. Here is only one force, yeah, and what is here, this is the process of bone remodeling, yeah, more or less. So if you have one force, the reaction will be like this, of course. It also depends on this here, of the size of the BMU. So for bone, this is some natural regulation, yeah? What you are able to do as a natural system, and your goal is to remove all degraded, or all structure with some problems, yeah, or some if something is wrong in the bone, you have to immediately to remove it, yeah? Yeah. So the size of this BMU is also important. In mechanical design, there is no problem, yeah, because you don't need to think how to do it, yeah, how to change this little part of bone in such a time and so on and so on. You just want to have some information how should be the ideal shape of the or form of the structure, yeah. So we can just neglect this old problems here and look only on the final result, yeah? How the bone will probably, if you will be able to do it from steel or aluminum, the structure will be completely different, yeah. Yeah. This complicated structure is the reaction of this value of strain energy density, which is allowed for this material. The material is relatively, not so good, because this is just something you have to produce from something you eat, yeah. And you have to change day by day whole your structure, yeah. So the structure is the reaction of the extremely complicated stimulation, mechanical stimulation, and from the other hand, this is the reaction which is just the possibility of building the mechanical structure inside your organism, yeah. So these two things decide that this bone is so complicated. Yeah, there is no other way to obtain a very stiff structure with this material. Yeah,
Yeah.
so you
Yeah.
with your bone material, and this is also very for me is really a miracle. Yeah, that you are able to build having the material was worth nothing. Yeah, if from this material you can build the bone which is really stiff. Yeah, when you compare the stiffness of the bone is comparing with the material properties, the bone is really stiff. Yeah, and this is also the automatically change the structure. If your sport activity increase, you will observe your bone are completely different. Yeah.
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 I see. Yeah. Okay. Great. And another question from me. Let me check the chat box. Okay, so I have time for another question. You build your own code or mesh generation tool, right? So
Yes.
that is the Cosmo projector, I think.
Yes.
And can you compare the results or the outcome of using your code with other methods or other codes? So to say, do you have a benchmark for your code?
Yes, you can find it here in these papers. I'm not going to present it now, but you can find this here in this work with Sokolowski and Zochowski. Yeah.
I see your 2018 paper, right?
Yeah.
Yeah. Okay.
And then you can find it, and we just produced completely different approach because our code finite element method is just used for the compute the distribution of the strain energy density. So we just produce our own mesh, and this we don't evolve the mesh. Yeah, every step is the new mesh. This is a little bit not so convenient, but convenient is that there is no problem with the element evolution. Yeah.
Mm-hmm.
So I have some experience with the evolution of mesh when we try to compute something in error elasticity. So if you once produce the mesh for CFD, you can be proud. Yeah. And then if you produce the information that the deflection is a little bit change this mesh, you have to change your mesh. Yeah. Mm-hmm. And there is the regular approaches like this that you put some spring analogy and try to move your mesh in your CFD computation area, and this is not so easy. Yeah? Yeah. If the changes is not so big, everything is okay, and but this is of course only to what extent you will find in your errors, yeah, and in the log files, and errors means that your elements are degraded and so on. So we assumed right from the start that we want to avoid these problems, and in our approach, every step of computation is with different mesh. Yeah? So I have two models. One, this is for finite element modeling. So I just produce the mesh for computation. And another one, this is the evolution of the geometry.
Yeah.
So this is completely separated. Yeah. So when I found the information that here on this area I should add some material, I added, but not by meaning of finite element methods. So adding some other elements or changing the parameters of this elements, but I just change the geometry and then go back to the mesh generation and produce completely new mesh. In this approach, this is also important that you can easily just produce holes, yeah, or just put some areas together. Yeah, there is no problem. Yeah? There is also a problem in when you level set method. If you try to use level set method, you have to start with some predefinition about this function.
Yeah.
So it means that your holes are more or less predefined. Yeah.
Yeah.
And here everything is extremely elastic. Yeah. In meaning of just evolution of the structure. Yeah. The separation or merging of elements of the structure, there is no problem. Yeah? This is another thing that if you for multi-load case, if you change the position of forces, you can do it at every moment of the computation. Yeah? There's no problem, because next step, this is a completely different mesh. So this is no problem just to change everything, like in bone. Yeah? So if you start some other activity, there is a structure, but the structure you have to completely change it. Yeah, just to fulfill this assumption that the strain energy density should be close to the homeostatic value.
Yeah, great. That sounds great indeed. So I mean, it's highly lecturers or your code. So yeah, sounds great.
So now we are trying to produce for EDAC something more close to the industry, yeah, because these examples are from academia, yeah, and they want an industry just the code. They want just to play the button, push the button and then play the process of optimization.
Yeah.
So we have to produce the graphic user interface. Yeah, so this is not so easy. And so on and so on and so on. Yeah.
Yeah.
So maybe it will be the reality, but this is the extremely difficult problem for programming. Yeah, just to produce the code. Everybody knows that SIMP approach is good. I think that you can now find some other approaches, yeah, like this one. But of course, I think that this could be done relatively simply, like I did with this code of Wole-Zygmunt, yeah.
Yeah.
You just skip the finding the right value of the Lagrange multiplier and put it as an input value. Everything runs with the same procedures. Yeah, so I think
Sure. Yeah.
this is a chance to introduce this approach to the real commercial codes. Yeah, of course, I can do it in Wole-Zygmunt code in MATLAB, and I just put 2 lines, yeah, and remove 3 others, and everything runs also good. And it is also possible for code like Ether. Yeah.
Yeah. No, that's fantastic, and I mean it's good to see that industry is interested in joining your code and work with you. I mean that's for sure fantastic to transfer the your research to, let's say, real world applications, right?
Yeah,
So,
yeah.
I wish you every success with that.
Sure.
Okay, so do we have more questions? I don't see any questions in the chat box. No one raised his or her hand. So that's it, Michal. Thank you so much for this very interesting and nice talk.
Thank you, Tom.
Enjoy the afternoon. I know it's very hot in Poznan, right, as well as in I think Europe. And thanks to everyone for joining the talk, and to all, happy afternoon, and we close the session now.
Okay.
Thanks again. Bye-bye.
Bye-bye.